Hi, Innovation Day. My name is Malak, and I'm a junior here at UTA. Today, I'm excited to be sharing with you a progress update on my project, WoundWare, which was initiated for last year's Innovation Day. So before we get into it, let me remind you of wound healing studies and where WoundWare left off last time. When scientists study wounds, they are seeking out ways to accelerate healing. For any biomedical research, it starts off in a small scale with cells, also called in vitro studies, and eventually builds up to animal and then human models. When experimenting with different treatments, macroscopic images are analyzed to view cell proliferation and migration for wound closure. Healing rate is determined as the open wound area over time, and the manual approach to segmenting these images is tedious. Often, scientists take shortcuts to produce inaccurate measurements. I automated this process by implementing UNet, a convolutional neural network that classifies images pixel by pixel to produce segmentations. With that, we were able to determine healing rate by calculating the area over a time series of microscopic images. To expand the scope and applicability of WoundWare, I wanted to generalize my model across different wound shapes and magnifications so more researchers can use it, since last year I only focused on one wound model. Furthermore, I wanted to develop a user-friendly interface. To train a machine learning model, we need a dataset, and since there are none for this purpose readily available, I compiled the dataset myself using Scratch and exclusion assays done in Dr. Cho's lab across different microscope objectives. A scratch assay involves scratching through a cell culture to produce a wound, and you observe how the boundaries change over time. And another wound model is called an exclusion assay, where you create a cell-free region by culturing cells around a barrier and study how the cells fill in the region as it's removed and as time goes on. I also expanded to multiple magnifications because some may use a more zoomed out 2.5x to view the overall wound shape dynamics, while a more zoomed in 10x may be used to also inspect individual cell morphology. Different microscopes also produce different image formats, so during pre-processing, I ensured that everything was uniform by converting everything to grayscale 256 by 256 pixel images, which is also important to be the correct input for my UNet model. To train the model, I created these segmentation masks to identify the wound and healthy regions, which it learned to identify the non-cell regions after. I originally yielded to train one model with all these images, but I found that creating a model zoo for each of the different wound shapes and magnifications have had a much better performance, probably due to the different features across these variables. So I have one for each magnification as well as wound model, and you can see some sample predictions from each of the four. For this year, I mainly focused on the 10x scratch images because that's what a PhD student, Mia, is using in our lab. So I did some benchmarking on a test set of images that she was using. For 48 images, so it was 12 wells across 4 different time points, it took her around 3 hours to manually segment and get her results. While with WoundWare, I was able to process all the images in less than 3 minutes. Here are some sample segmentations WoundWare produced side by side with the masks that Mia hand segmented. Here I also show the intersection over union metrics, which is common for segmentation benchmarking. The closer to 1 means that the prediction overlaps with higher amount with this hand-segmented image. I noticed that T24 has a lower IOU score as the boundary becomes more variable and complex to define. I also do have fewer images of scratches that are in the later stages of healing, but I continue to add images to the training. I expect this IOU score to be as high as the others. Now that I generalized the model to fit across the 2 of the mainly studied wound assays and magnifications, I implemented a Google Colab notebook and an ImageDay plugin for model use. For the Google Colab notebook, it's as simple as uploading the trained weights and all the images that you need. For instant segmentation, and if you provided a time series, it can also calculate the healing rate. And a good thing about Google Colab is that it also offers free CPU and GPU units regardless of the user's hardware. On the other hand, ImageJ is a software widely used by life scientists for image analysis. Especially for biologists who may not have extensive coding experience, Colab might be uncomfortable to use. There is a plugin on ImageJ called Deep ImageJ, which enables developers to package their models into a format that can be run with PyTorch frameworks. After easily installing the plugin, all you have to do is install WoundWare with the provided zip file and click Run on any image that is open to also produce instantly segmented images. With that being said, I was able to complete the objectives I set out to complete this year by generalizing the model and achieving sufficient metrics to speed up analysis time, and by creating user-friendly tools for people from any background. In the future, I hope to compare this to any models that may exist already and ultimately complete a wound healing study with fully automated analysis. Thank you so much, UTA-REU, for supporting this endeavor, as well as Mia for providing insight into wound studies and much of my scratch image dataset. Once again, thank you so much, Anne, for everything you do. Thank you so much for listening. Bye!